Okay, welcome everyone. It's my pleasure to introduce Bernd Scheuchl. Bernd got an engineer's diploma from the University of Graz in Austria in '98, a PhD from University of British Columbia in electrical engineering in 2006. He had a work stunt at MDA in Canada and Aperture in Germany before joining UCI in 2009. So he's been here for 14 years. As a project scientist, he worked on the Measure project, which has been funded for 15 years, and we hope another 5 years. 20 years of NASA funding. That's pretty cool. Measures is a program at NASA that makes Earth science data products for the community from the satellite mission. So we've made ice motion products in the Antarctic through the Measures project, and Bernd was a key member of the team that put this product together since 2009, and the products are used worldwide to describe what's happening in the Antarctic. He's also a PI of a new investigation with ICE-I, a commercial constellation. He's a co-I on numerous projects. He's been mentoring a lot of our graduate students over the years, and is of course a key member of our group. He's going to talk about virtual satellite constellation, which will give you an appreciation for where we started from and where we're going next. There's been a large evolution of the field in the last 15 years, and it will trace that back to you. Thank you.
Thank you, Eric. Good afternoon, everyone, and thank you for making time to listen what I will be talking about. Before I start, though, Eric mentioned that I'm one of the team members, and I want to dedicate this presentation to the other team member in this. There were three of us that started out, Eric including, and we lost Jeremy last year. We're still sort of, well, there's no really getting over it, but we're still working sort of towards accepting the fact that he's gone. And that's not made any easier by the fact that whatever we touch has his fingerprints on it, partly literal, partially just in terms of how much he contributed to the effort. We are talking about ice sheets with respect to the observational record, and so I guess we could boil it down to two key questions. The first one is, are the ice sheets losing mass? And the second one is, how do the ice sheets react to climate change? And ice sheets, by definition, they are defined by size, and in a way that there are two ice sheets on planet Earth. One is in Greenland, the other one in Antarctica. The sea level equivalent of the two are shown here, meaning that if all the ice were to melt, we would be looking at a corresponding sea level increase. I don't think anybody would think of that that's the case, except for a really, really bad environmental scenario. But some of you oceanographers would enjoy that and have sort of more area to work in. So why should we care about ice sheets and the record? It is sea level rise, I already mentioned this, and this is a graph from the synthesis report of the IPCC that came out in March. And it shows here that we have a number of scenarios in terms of CO2 emissions and warming, and how that will impact mean global sea level rise. One of the aspects that I see future work is to decrease the uncertainty of the estimates of sea level rise, because there is nothing worse if you tell an engineer build a 1 meter, protective berm around a coastline or a harbor, and you find out that he's 20 centimeters short. So that's a big aspect in terms of adaptation. So sea level has increased in the last 120 years, and the rate of increase is going up, so that's a bit of a concern. And the risk assessment of the report shows that we are looking at extreme sea level events projected pretty much everywhere on the coast, or more than half of the type gauge location. So meaning we are past the point where we are preventing sea level rise, we are adapting to it. And so for adapting, it is important to have good estimates. So how do we measure mass balance of the ice sheet? So we want to know, is the ice sheet losing mass? One aspect, measure it directly, and that's done through gravity. I'm not the expert in this, but we have an expert in-house on this topic. If you want to know more, talk to Isabella on that topic. But what the record shows, what the Grace and the Grace follow-on mission record shows, is that yes, indeed, Antarctica is losing mass. It's regionally different, and so there are regions that are more affected than others, but overall, that's the message from gravity. The second one is, the method is altimetry, so measuring digital elevation models, in this case from space, and taking the changes in elevation, calculating from those changes mass loss or mass gain. This is more regionalized than gravity, so that the resolution is also a bit higher. But in the end, this particular method suffers a bit from snow falling that compacts, and you have to account for the firm compaction. And so that model, there's a bit of contention whether or not this is done right at this point in time, and I will get to that in a bit. The third method, we have another expert in-house, and the person has just introduced me. This is the input-output method, where you take a regional climate model for the surface mass balance, and you calculate using ice velocity, ice thickness, and grounding line information. You calculate the flux, sort of how much ice is going into the ocean. So you have input, output, and sort of that gives you information on the mass balance on a glacier basis. It's the most regionalized method. In addition to the mass balance, you also get information on the changes in speed of the glacier. So you have more additional information about the ice shelf than with the other two methods. So how do these three methods compare? In principle, very well. There are some regions, or there's one particular region, this is East Antarctica, where there's more discrepancy than one would like, but there are potential explanations for that discrepancy. But this intercomparison sort of framework is ongoing, and there will be a paper coming out tomorrow, so keep your eyes peeled on press releases that should be coming out tomorrow on sort of the latest iteration of this particular type of work. So the strong impact that this type of work has, in my mind, is that we have three different physical measurement principles that we use to measure the same thing. And if you draw a line at zero, you would see that overall the answer to the question, are the ice sheets losing mass, is a resounding yes. And that has obviously impact on sea level change and our projections. So now the question is, one, how much mass are they losing? So to bring down the error bars in those estimates. And how do we do that? Well, we have some ice sheet information requirements. Ice sheets are acknowledged by the UNFCCC, sort of the UN Climate Change Organization, as an essential climate variable, and we have defined information requirements. This is sort of a subset of that. We need surface elevation and elevation change. I've shown already that we could use altimetry, but there is another sensor that can be used. We need ice velocity, or information about ice velocity and changes thereof. The grounding line location and also the migration of the grounding line, as well as calving front location, calving rates, and last but not least, bed elevation. And I put these here in particular because we are looking at observables that directly or indirectly can be measured with synthetic aperture radar. The first one, elevation change, needs a specific SAR mission to do that. And bed elevation is sort of a derived product based on ice velocity and other input sizes. So that's why I had that sort of put it down in italics. So the method that Eric's using is, again, surface mass balance as input. So how much ice is produced minus what's melting on the surface. And that compared to the ice discharge. And the ice discharge is the measurement or the calculation that we do based on grounding line, ice velocity, and ice thickness. So synthetic aperture radar, some little bit of history on missions. The first sort of civilian synthetic aperture radar satellite was launched by NASA in 1978, called CSAT. Unfortunately, the mission only lasted for 3 months. So there was some science coming out of that already, but certainly 3 months was not enough time to make a lasting impact on sort of the science of this particular type of sensor. I should mention in 78, Landsat was already in its 3rd generation, and it took another 13 years before the Europeans launched the first sort of agency synthetic aperture radar satellite. So it was the early 90s when things started to really develop. The Japanese started a satellite, the Canadians launched a satellite. NASA was focused on shuttle-based radar missions. Those were shorter in duration, but had sort of advanced radar, so multi-frequency, fully polarimetric radar missions. So there was a component that NASA contributed, but only focused on the orbiting kind, or sort of the satellite kind of mission. This is an image. On the left is Los Angeles monitored by, or imaged by CSAT. And what I always found curious is that Burbank lights up like really distinctly in that region, and it just turns out that the street, sort of the grid, is slightly rotated to the rest of the region, and that was enough. That's parallel to the radar flight direction and orthogonal to the loop direction, which means that a lot of the signal from Burbank goes actually back to the radar. This is a RadarSat image that I used for a course way back when, and I apologize, I don't know the acquisition date. This is the Strait of Gibraltar. And I like that just for the pure aesthetics of the image, because you see potential ocean applications, you see internal waves, you see ships, ship wakes, you see slicks. There's land applications that are potential. It also shows sort of this weird geometry that the radar image has, where mountains seem to be leaning to the side, which is an effect of the radar not measuring sort of an XY coordinate, but really only the time it takes the signal to go to the target and back. So the coordinate system is slightly different from an optical image generation. But we're looking at ice sheets, so I just felt this was sort of gives even indication that radar can do a lot of things, and there are actually a lot of applications which I will talk a little bit about later. This is a high-resolution time series of Terasar X images, and I'll try to start that. And next to it is a time series that we worked with David Small from the University of Zurich. This is the northern part of the Antarctic Peninsula, the Larsen Sea ice shelf, and you see here the breaking off of the iceberg, D68, I believe, is what it's called. But it also shows you that you see sea ice in that image and the motion of sea ice, so that's a huge application for radar satellites. The Canadian radar program came out of the need to monitor Canadian waters and provide ice charts. And RadarSat-1 changed the way the Canadian Ice Service was producing that. And the RadarSat program since has continued to be a stellar example for an operational application. But, oh, sorry, I just saw that I moved. Sorry, this should not. Radar just is not just an image, you know, and it's black and white, so the younger group here in the room is probably not too impressed. I still think that sort of a grayscale image can have a lot of information, but radar offers more than just sort of the backscatter strength. If you take two images, turns out that the phase of the signal, as you know, you send a signal with a specific phase of a single image. It doesn't tell you much because there is a random component on the ground as the signal gets scattered back. But if you take the difference between two images and form the phase image, turns out that this phase signal is sensitive to atmospheric changes. It's sensitive to the imaging geometry, which is a bit of a nuisance, but it's something that can be modeled and can be taken out. Atmosphere could be nuisance, could be signal, so that's in the eye of the beholder. What's most interesting to us is it's sensitive to topography, so it can be and has been used to generate visual elevation models, or to collect data to generate visual elevation models. And it's sensitive to displacement, and displacement could be subsidence or glacial motion. And in 1993, two landmark papers were published, one in Nature, the other one in Science. And the Nature paper sort of made it on the cover of Nature. This was an image of the aftermath of the displacement based on the London earthquake. And what was so impressive about this was that the pattern that you see here, this is the phase signal, perfectly fit the model that they generated based on the earthquake data that were collected. And to this day, if there is an earthquake somewhere in the world, people will look at, do we have an image before the earthquake and an image after, can we sort of generate this type of information. So earthquakes continue to be also an application for INSAR. The one that I'm more interested in was the other paper published by Richard Goldstein from JPL, and he showed that with this displacement you could monitor ice sheet motion, translation motion, and he did that with the phase. It turns out also that, and we saw that probably from the animation before, if you just track the pixels, it's enough where you can get an offset map. And the advantage to just tracking pixels, and in this case, there is a specific property of a SAR signal that's called spectral with an active instrument. So the signal will either be constructive or destructive in how strong it is, and this can change from pixel to pixel. And provided there's not too much change in the ground, this spectral will stay the same, so we don't rely on features necessarily. Yes, features will also play into it, but there's also this spectral that will provide information. And spectral tracking is the method that we started using because it has the advantages. It's slightly more robust, and it needs less data because we have the two components in look direction and in flight direction from two images. So this displacement. But based on this information, young researchers at JPL started doing, digging in and doing the hard work and sort of laying the groundwork for research in ice sheet science. Eric published, has an impressive publication record from, and he had done work before, but I think it was the INSAR component, so the phase component on glaciers that really changed the way in terms of he looked at science, and even what he does now. He's now a full-blown glaciologist, so this was just a means to get him in the field. But so with this publication record, by 2000, there were, 97 was a major campaign by the Canadians, sort of suggested by NASA, who had launched the satellite Regasat 1, to map Antarctica and create a backscatter map. That was actually the first map of the Antarctic continent, sort of with the radar, and was an impressive achievement because it needed the sensor, the satellite, to sort of turn around and look the other direction. The sonar looks to the side, and nominally this one would look towards North Pole, because that's what they were interested in, but we would look away from South Pole at the same time. So this, in order to achieve this, they had to get their brand new toy, turn it around in orbit, and make this happen. There were some INSAR acquisitions of opportunity at the time, and there have been publications on that by one of Eric's colleagues, Ian Joplin, who's at the University of Washington. And between the two, they sort of dominated the field in terms of interferometric acquisitions and analysis of ice sheets using INSAR data. And this came together, so we had some large-scale acquisition campaigns, but they were one-offs. This came together with a solicitation at NASA in late 2006 through the Measures program, where you had to have your science in order, so the algorithms had to be proven in order to suggest that we are going to produce geophysical information product based on that data. So Eric was funded, and that's when things really started. At the same time, the International Polar Year around that time happened in 2007 and 2009, and space agencies started to, in support of the International Polar Year, started to acquiring data more frequently in the polar regions. But we also sat together and said, how do we coordinate this in order to avoid duplication of effort and in order to avoid some gaps. So there is a coordination effort going on, and once the polar year was over and we had benefited from that, I got involved and became the ice sheet science coordinator for that group. And I have to say, even to date, there is no single SAR mission that's a pure science mission. There's always a competing and not only competing, a dominant interest. The Sentinel program in Europe is a decision-making system for the European Union. Regasat has dominance of monitoring Canadian waters, and so on and so forth. So there is, science is an afterthought or maybe a component of the mission design. So Eric hired Jeremy and myself, and in his proposal he wrote, I'm going to do this for all of Antarctica, and he told us around this time that he wasn't sure this would work. So we were basically more than a year in to find out that when the proposal was written, he had the tools in order, but there was not enough information in place to say, yeah, for sure this will work. And this was the IPY conference in Oslo. I think this was sort of the finale of the International Polar Year. And the space agencies invited Eric to come and show what we had. So this was the first map, and looking at it now, it was this looks really awful. It's not calibrated. You can't use this as a science product, and we knew that. So but it also showed us, hey, this is going to work, and not only is it going to work, but we will achieve content by coverage. And so we did. This took another year. More than a year, actually. There was more data to be processed, but it really was sort of an iterative calibration process to make sure what we're measuring is sound and neighboring tracks actually don't show up as tracks. So this is the first version of the map that was published in 2011. And all of it funded through the First Measures project. So not only do we have a science product, Eric became also the first user of his own science product by looking at adding additional information on elevation and elevation changes, but estimating the ice shelf melt and the sort of distribution between melt and carbon in Antarctica. And this is a landmark paper because for the first time there were hard numbers behind, you know what, melt is actually a pretty important component, and it's larger than carbon in some areas, and in particular areas that are quite vulnerable. So knowing that, the ice-ocean interface became a much more interesting, or much more important component to look at. The second user became Matthew Molicam, and when he was here at UCI, he had developed a method to take ice thickness measurements that were essentially flight lines, and in the past were more or less crudely interpolated together to sort of have a map of the bed underneath the ice shelf. And he said, we can do better. We know sort of some of the physical principles involved. There is a method, mass conservation, that was first proven by Ellen Ceruzzi. And Mathieu took the idea and sort of proposed a project to use that in fast-moving areas, so use our velocity map for fast-moving areas, apply that concept and apply other concepts that are more suitable in other areas. So the product is now, I believe, in iteration 5. He provides error maps. People who use it should take it with a grain of salt, but they should look at the product because he tells you where the product is good and what sort of information went into which method was used. So you can basically judge very well whether or not the data that you have, it is a reference product, but there are still words that, just a lack of data necessitate that you need to take this with a grain of salt, and I guess that's with every information product. We then started looking at time series and differences. And differences were my first nightmare in this project, because when we form the difference, you're not looking at 3 kilometers. So neighboring tracks, an area of 10 meters would pop out like in the velocity map. Not a big deal because it's a sub-percentage, but in the difference map, it started to pop out. And so that taught us that we have to be really careful in how we go about calibrating these single tracks and this myriad of tracks. And in addition to that, I also had the pleasure of working on a paper authored by Bob Thomas, former NASA cryosphere scientist and I think mentor of Eric. And we were able to take the record back to the RITS, the Ross Ice Shelf survey. These were measurements on the ice shelf sort of before GPS. So it was pretty cool to work with the data set of that era. The next time series was a bit more involved. This is the Amundsen Sea embayment, and some of the key glaciers in Antarctica. Thirds Glacier is the Doomsday Glacier. Not that I like the name, but people will have heard that name more than Thwaites, I guess. And Eric showed that we had measurements of the grounding line. I will talk a bit more about the grounding line in a second. In the 90s, and then a specific campaign of ERS-2 that was geared towards the grounding line measurement in 2011, and it showed that this glacier is receding, so the grounding line is moving upstream, and that's not good news if you remember back the ice sheet bed. So the Thwaites is the bed is under sea level, so ocean water that reaches under this glacier has no natural stoppage in a sense. We also did the time series. This is just a difference map, but the record was taken over 40 years, so trying to use older altitude data to try and get a speed record that reaches back 40 years. We continue to work on sort of the time series aspect. The product that we have now is annual products, but we're looking at monthly products as well. And we're learning new things as we look at subannual variations in Antarctica. There are publications coming out now that the peninsula shows subannual changes, but we also see that on Pine Island Glacier, and sort of there are questions, so what is causing that? And there are a ton of research questions that a denser time series will open up and sort of foster new research. We have two philosophies on our velocity products. One is the maximum coverage possible. For the reference map, we strive for 100%. I think we're at 99 point something. The other one was to have timestamps. And this product now is sort of a compromise where we have different time periods and reference time periods. In the future, this is not going to be such a big problem because there's more data available, but for the past, the three oldest ones, this is a big deal where we took three to 5 years and generated this. And again, sort of the interest here is to look at changes in the ice sheet. The difference map also showed us some limitations with this tracking method because we don't see changes as far upstream as altimetry records indicate that changes should be. And we have been working, so remember when I said Goldstein in '93 showed that the phase is sensitive. Well, the difference here is the phase is sensitive in one direction only in the look direction of the radar to displacement. So we need acquisitions from two directions, and in order to get to an interferogram, we need two acquisitions. So we need 4 acquisitions at the very least to make this measurement, and took sort of with the acquisition in the past, it took about this is a 20-year data record. Most of the data were acquired within 10 years, but in order to get as much coverage as possible, we extended the record back. This is again a reference product trying to get as much coverage as possible. The improvement is significant, is an order of magnitude, so we are now in the order of centimeters per year motion of error. So we're getting closer to the basin boundaries and to the divides. The grounding line is where the ice meets the ocean, so where the ice starts lifting up because it starts floating on the ocean. Eric has done, and I showed some research on this in Greenland and also in central Antarctica. But we didn't have sort of the continent-wide view of this, and part of the measures output was continent-wide grounding line, and as you see, sort of divided by year, it's quite a mix between 92 and 2014, but also a mix between sensors. Sentinel-1 changes that a little bit, where we have now regular acquisitions. And we also find that because we have regular acquisitions, we measure grounding lines multiple times a year. And we find that there are short-term migrations of that grounding line on sort of tidal scales. And I see some students rolling their eyes because that's what they have been working on for quite some time now, and trying to figure out, what does that mean? This means that we have potential access to more ice by warm ocean water. That's one consequence. The other is we are looking, how do we interpret single measurements in the past with an ensemble measurement, where we know that we have sort of a grounding zone width that's actually bigger than we expected and bigger than what models suggest. The next sensor family that came into the fold was Italian Constellation, Italian Space Agency in the private sector, Cosmos Skymed. Pietro Melillo is PI with the agency, and we worked with him on publications in the Amundsen Sea. Virginia Brancato was a postdoc with us, working on Denman Glacier. This is an Antarctic glacier in East Antarctica, both also showing grounding zone measurements in very fast glaciers. The advantage of this mission is that you have one-day repeat orbit, meaning that there is a chance to get a signal in fast-moving glaciers. This is the most recent work. The paper will come out in the next 2 weeks. Enrico, who's here in the room, has been working extremely hard to work with older data, that's ERS, that's European Space Agency data, as well as Cosmos Skymed. And we also brought an industrial vendor on board. Actually, they approached us to see if there is interest in capabilities they have to offer, and based on our experience and based on what the their constellation had to offer, we said a resounding yes. So that's a collaboration that's going on. And Enrico also managed to estimate the subglacial melt in the grounding zone, and as you can see in the plot, that it's actually, the melt rate is quite high in the grounding zone, and there's potential for subglacial channels to have an impact on this. The title says virtual constellation, and what do I mean by this? I mean, a satellite constellation means they're sort of lined up, or the A-train, I think, was an example that was in NASA or NOAA. So a series of satellites making different measurements, but they were in the same orbit. There are satellite constellations, Cosmos Skymed being one, and ICEYE being another one. Sentinel is a 2-satellite constellation. But what I mean is to take an acquisition plan from one agency, overlay it with an acquisition plan from the next agency, and make sure we don't have any observation gaps. We're getting the most of the available data. And that allowed us to make sort of recommendations to space agencies where to acquire data, and in terms of, if I do here, well, you acquire there, or if you acquire there, I don't have to, that kind of thing. I should say that Sentinel has long-term funding, so that's the first really sort of operational mission. There's a 30-year funding envelope that I'm aware of, meaning that goes beyond one generation of satellites. And that's part thanks to it being a decision-making tool for the European Union. The Japanese, I had a graph on that, their first generation, it's a second generation satellite, but the first generation pulsar, had huge impact on our first map. Unfortunately, the ALOS 2 pulsar 2 had more restrictive data policy. We still are able to access MPI for 2 projects with data support. And this is an L-band mission, so it will be the same frequency band as NISAR. I'll talk about NISAR in a second. So we use that in order to assess the potential utility of NISAR, and I mean, not the potential, but the utility of NISAR, and maybe even find some of the issues that we will find at the mission based on this data. I mentioned the Canadian program, and there is a real legacy in Antarctica. The very first map acquired in 1997. 2000 had sort of an interferometric acquisition campaign, and we reprocessed that, so that's part of our annual time series. Since then, sort of RADARSAT-2 contributed, you see sort of here in the center, these color plots, and that's just where data acquisitions were made. Some of this was gap filling from maps that we had, and some of this was just an attempt to fill in. In 2013, the purple is an attempt to replace NVSAT and ALOS, because within a 2-year time span, we lost 4 out of 5 missions that we had used. And so we were looking at a really dire situation before the launch of Sentinel. And the future, the Canadian program, RADARSAT-2 is still active, and we still receive data. The future, the next generation is RCM, the RADARSAT Constellation mission. It's a short repeat, and short repeat is good for grounding line measurements. They didn't have any plans for acquisitions in the southern hemisphere, but we were fortunate that, well, not fortunate, but with the effect of one of the Sentinels going down, ESA asked the Canadian Space Agency for help with CA's acquisitions around Antarctica, and that opened the door for us. And Eric was at the conference in Frascati, where he was able to convince the manager that this would be useful. And because we had done all this lobbying work before, we had basically, he asked me, do we have a suggestion for them? And I said, I was able to send it to him basically right away. And that started this, and we have first results. Enrico worked with me on the processing workflow, because there will be data coming in more regularly, and that means we don't want to download by hand, process by hand. It should be a very automated process. And we have basically most of the elements in place already. So that's the present and near future in terms of the one very exciting future component is NISAR. This is a NASA collaboration between NASA and the Indian Space Agency. It will be a dual frequency radar, L-band and S-band. 12-day repeat orbit, global coverage of land masses, and more importantly for us, it will look to the left, it will look towards the South Pole, so it will cover most of Antarctica every 12 days. NASA, this will launch in early 2024, so the satellite is in India already, the Indians are launching it. There are launch preparations going on, and at NASA, there is a growing momentum in terms of supporting the radar community. So there will be funding calls coming out this fall for science PIs, but also for the operational science team. Both Eric and I are members of the Cryosphere science team for NASA, preparing the mission for launch. So NISAR is, I mentioned it here, a Pathfinder Earth System Observatory. And what is that? That's sort of the NASA's response to the Decadal Survey. And they're they will build a series of observation platforms. And one of them is SDC to respond to the observables identified in the cable survey. One of them is surface deformation and change, which is another name for an ISAR follow-on mission, essentially. But it sort of follows the very similar development pattern. There is a role for a growing commercial sector in terms of remote sensing, satellite data providing. So, sorry, SDC, like NISAR, has a host of applications that people are looking towards. But that also has sort of development and funding opportunities, that program. And as part of SDC, NASA is investigating several mission concepts, and they're also looking into the commercial sector to see if commercial data could be useful to satisfy some of the observables that are needed to help the mission either achieve its requirements at lower cost or relax some of the requirements because they are satisfied by the commercial sector and be able to focus on other requirements with the NASA mission. So there will be a NASA mission, commercial or not, but there is a component. And I'm involved in sort of the evaluation for SDC, of the commercial sector for SDC, but I'm also, NASA is also has a program for commercial small sat acquisition program that identifies, does it make sense to buy data from this vendor? Can we advance our science research and application goals? And I've been selected as PI for evaluating ISAI data. So going back to where I started, we have two key questions. Are the ice sheets losing mass? I think the community has responded to that. The question now is, how much are we losing? Can we narrow these error bars? How do the ice sheets react to climate change? Well, I've shown sort of our Earth science data record shows that we are looking at dramatic changes. But this is still the big question. I think this is the area where we're working on the answers. So we have partial answers, and this needs a mix of hindcast, I call it, to look at historic data sets, trying to preserve them, trying to take new methods that we have now available to squeeze as much information out of them as possible. Nowcast to make sure we have acquisitions and we acquire the data, because a data set not acquired is a data set lost forever. So if we want to keep our hand on the pulse of the planet, we need an observation record. And then forecast, this is essentially the modeling community being challenged to then make these predictions based on what they know and also what the observational community knows. So we are observing dramatic changes. New mission capabilities open also new aspects for research. Denser time series, what are we looking at? All of a sudden we are seeing sub-annual variations in Antarctica. That doesn't mean it wasn't there. In some cases it probably wasn't. In other areas it might have been there for a long time. We just didn't have the data to see it. The Measures program funded Eric and myself in turn for 15 years. We have another proposal submitted and are waiting news on the decision, on NASA's decision on how this goes forward. The other news is, and whether sort of if Measures is funded, NISAR will play a huge role in how we go forward with this Measures project. but NISA will provide huge opportunities for research, regardless of the previous mention. I mentioned the calls coming up in the fall. The data are free of charge. There will be level 2 data produced that are currently being defined and sort of implemented by the science team. So a lot of processing that Eric, Jeremy, and I did will be done by the project. And so that will free up people's time to actually take the data and answer some of the questions. What are we looking at? Why is that happening? And so on and so forth. With that, I want to thank you again for your time. This is just a listing also of the Earth Science data record that came out of the Measures project. This is available at NSIC. This is a formal NASA archive. And so our work, Jeremy's work, my work, Eric's work is preserved through this particular mechanism. Thank you.
Questions for Bernd?
Are there any questions?
From the audience online, I don't know how we handle that.
Okay, sorry,
That's a good question.
Oh, yeah, so you mentioned Bernd, very nice, amazing data product and used. I hadn't heard until we chatted this morning about the sub-annual behaviors that you're now able to piece together with more recent observations. Could you say a bit more about what we're learning on sub-annual timescales, on grounding lines, for example, or wherever the data are most interesting at that timescale?
So on grounding lines of this sub-annual observation and sort of the tidal scale migration of the grounding line, this is not a retreat, this is moving back and forth, means that we are now defining a grounding zone, meaning that there is an area of the ice sheet where ocean has partial access. With the tide going in and out, there are quite high speeds of water transport, and that may sort of impact the rate of melt. The grounding zone also is, so we have one measurement in the 90s. So we need to put that into context of the grounding zone. So where does this fit? If we have one glacier, and one of our students is currently working on this particular region, where within a tidal cycle, the grounding line migrates up to 18 kilometers. 18, and it's an outlier, but it is in a kilometer range quite often. 18 is, is a drastic example. But 18 kilometers, if we had one measurement in the 90s, and then one measurement in 2011, and we didn't know that the grounding zone was 18 kilometers, and we say, oh, we measure retreat, when in effect it's only part of this sort of tidal scale migration. Fortunately, all the retreats that were reported in previous publications, it showed that the grounding zone is actually smaller than the level of retreat that we reported. So it was, I guess the measurements were far enough apart for the changes to take place to say that this was a signal and still is. So on the velocity part, in Greenland we had known for a while, and there is sort of a whole host of research going on with respect to how does subglacial hydrology play a role in lubricating glacier during summer months where there's more surface meltwater that finds its way to the bed and then potentially lubricates that glacier. Jakobshavn, I think, speeds up significantly in the summer months, for example, but it's definitely not the only one. Shivani, one of our students, just recently published a paper where she was able to replicate observations with a model, which is not a real easy task. So, but you have sort of these internal variations, and she's looking at hydrology model, phase sheet model, and sort of putting that together and making sure that the model output looks close to what observation shows. So you have
So I guess we kind of ended saying that we now have maybe 2 to 3 decades of mass with reliable mass change.
Yeah.
Are we close to building a reanalysis products? Like, for instance, what we do in atmosphere.
Okay, that's a good question. Are we close? Are we close enough with a 30-year record of ACE mass balance to build a reanalysis product? So is the satellite record close enough to sort of look at reanalysis concepts similar to what climate models do?
Talking about the reanalysis data or incorporate satellites around?
I'm not sure if I got the question.
Go ahead, no.
Did I understand the question? So, is the satellite record long enough? Could we look into? So you model the mass balance. Could you do reanalysis based on?
But the satellite data are part of the reanalysis record already. There's all kinds of satellite data that go to reanalysis products.
Right. No, but I'm saying that for atmosphere and ocean, we have now, over the years, slowly gone back and reconstructed, and I guess self-consistent, dynamically self-consistent reanalysis products. In the context of mass balance, especially for glaciers, can we go back?
But it's a measurement, so I'm not sure if that's the same.
I think what he's
We went
saying
back
is,
40 years, as far back as the reanalysis data go.
has your model
We go
evolved
back.
during this time? Has your model evolved? I think that's the question.
In part, it's related to that too. I mean, because.
So if you went back and used your current model on old measurements, or
use old measurements and create a new reanalysis. The
exactly,
reanalysis did not use your mass balance. You make a data-driven mass balance, and the reanalysis makes a model and some data mass balance. Could they be blended together and redone? That's what you're asking, right?
Yeah.
To do better even. Both would be improved by merging.
But the reanalysis data are used in this mass budget.
Yes,
To
but
think about the mass balance of the ice sheet, you need the surface component. So that's the surface mass balance from reanalysis data, and then there's the ice component.
yeah, but the question is on the ice components.
Yeah.
The velocity of the ice.
Yeah, so we go back to the beginning of the satellite era, which is the 70s, Landsat.
Right, so you're up to date.
Yeah, we did that.
Okay.
We go as far back as there was a satellite with a dog in it. And collected data.
can I ask another follow-up question? So that means that the error in the reanalysis mass balance is exactly, or not exactly, is a part of the error in the outflow.
Yeah.
You just take the difference. You don't have an overdetermined system, I guess is what I'm saying.
Yeah.
Where you put them both together and you'll beat down the errors of both. They are
Yeah, so,
independent components.
yeah, so these budgets compare two big numbers, what comes in as mass
Yeah.
and what comes out. So most of what Bernd described is what comes out. And what comes in is reconstructed by climate models. And since 2006, these climate models have been, they made major strides in doing this right. To the point where we don't need to go in the field to check them out. We don't. And this was announced back in the early 2000s, and it's true today. Going to the field to check them out is useless.
The models are so
They
good.
are right on with some inaccuracy at a few percent level. But compared to what we had when we started this project, it's I would say check. check on that. We're refining at the regional level on some local processes, what's happening on an ice shelf, what's happening at high resolution, all that stuff, but it's not gonna change the big numbers. This is fantastic. I still don't believe it. I still am amazed every day that these models get it right. Because we all know climate models are never right, but for this reconstruction, they're doing an amazing job. Amazing. And now they do it on a monthly basis. We get update every month globally. It's mind-boggling.
Well, there was one question during the discussion, what resolution is right now?
It's typically 25 kilometers.
Okay.
Okay, so it's Rockmont.
But right now it's 11 kilometers.
11.
We can go down to 5 kilometers, and after that, the physics breaks down. They cannot do it. 5 kilometers is their limit.
I have one more if nobody else has this.
You mentioned these grounding line retreating 25 kilometers. Does anybody run tidal models with kilometer scale horizontal resolution? You would think that that would affect the dynamics of the tides. The fact that when the wave comes in, it has to lift the ice sheet and then it hits the ground. And is anybody looking at these tidal models, or the bathymetry is so uncertain that?
So I
it's not
think the issue was with bathymetry in terms of we talked to Laurie Patman, who has one of the leading ice sort of tide models. And we use tide models. Hanning just recently did a comparison where the INSAR measurements fit the tide model quite well. I'm not sure on the local scale if there is a feedback mechanism to sort of say maybe that has an impact on the model. So no, I don't think, and partially also because that's sort of the recent development that we have that grounding zone product. And we're still sort of wrapping our heads around, what's happening. So people in the community still misconstrue what we talk about grounding line. There is some confusion that some think it's the flexure zone of the shelf. So the portion where the shelf is bending. That's actually something you see in the interferograms that are used for grounding line measurements, but that's not what we're talking about. This is literally where the ice lifts off, this line moving back and forward, and that's driven by tide.
The tidal models don't do well in the cavities because the cavities are not well known.
Okay.
That's a small. Okay, I think we have to wrap up. Thank you, Bernd. Thank you for